Good afternoon, all. Once again, welcome to the third session for the AICT and AQIS sponsored Computational Fluid Dynamics, role of Computational Fluid Dynamics for engineers. And today we are the third session, and today's speaker is third session speaker specifically, Dr. Absar Lakdawala sir. It's my pleasure and privilege to introduce Dr. Absar sir. Dr. Absar Lakdawala is working as an associate professor in Department of Mechanical Engineering at Nirma University, Ahmedabad. He is having experience of more than 18 years in the field of teaching, research in industry. He obtained his MTech degree in thermal engineering from IIT Delhi in 2007. He obtained his PhD degree from IIT Bombay in 2015. He has published more than 15 research papers in the area of multi-phase flow, computational fluid dynamics, and alternative fuels, etc. Specifically, he has published all these papers in international journals, and he has presented and published more than 30 research papers in international conferences as well as proceedings. He has successfully executed 3 research projects as a PI as well as co-PI funded by Nirma University and the Gujarat Council of Science and Technology in the area of alternate fuel for IC engines. He has guided more than 36 PG dissertations. He is presently guiding 4 research scholars towards their doctoral degree. Mr. Lakdawala is a reviewer of international journal in the field of multi-phase flow, fuel, etc. He is at consultancy, research and testing in the area of mechanical engineering. His research interests include computational fluid dynamics, multi-phase flow, thermal system simulations, and design and fuels. It's really a pleasure for us, sir, being with us. And I knew him personally very well. He's a really good speaker, and I'm pretty sure that we will enjoy your session. Thank you, sir. Lakdawala, sir.
Thank you, Mitesh bhai. Thank you, Bala sir, and the management for inviting me for this lecture session. Should I share my PPT now?
Yes, sir. Yes.
I hope that the PPT is visible.
Yes, sir.
Yeah. So, in fact, should I start the talk or?
Yes, sir.
Yeah. Okay. So, thank you once again for such a nice introduction and the management for inviting me for this STTP. In fact, the STTP is all about computational fluid dynamics for engineers. And I hope that many speakers must have talked about, because I may not be the first speaker, so the earlier speaker must have talked about a bit of computational fluid dynamics. So what I have planned today is mainly related to application of CFD in a fluid flow and heat transfer, mainly the work which I have carried out at Nirma University along with my PG and PhD student. So I thought that it would be great to share some of my experience related to CFD, specifically in fluid flow and heat transfer with you all guys. So the presentation would be like this. First of all, of course, just to introduce what is CFD and why the CFD is required and all, which is basically a usual stuff. Modeling aspects of the CFD, mainly what actually we are looking for when we say mathematical modeling. And then there are various numerical methods available. So I'll just, I'm not going into detail of it because it is bit mathematics. So numerical methods, a bit of numerical methods and how we can use different kind of techniques to solve the problem in hand. There are various CFD codes available. So I'll just introduce what are the code available. So the user can definitely use some of the free code available to solve the problem in hand. There are some CFD educational interface available, specifically ANSYS has provided nowadays, even COMSOL has also provided educational interface, wherein you can interact with the company employee and you can learn the tool, which is an elegant tool. And in fact, it's a multi-physics environment available in COMSOL and ANSYS and Workbench. CFD processes, basically I'll like to explain and discuss the CFD processes using various examples. As I said, that some of my problem which I have solved using some of the tool available with my lab. So basically in physics, basically, or in engineering, any problem in hand can be handled by three basic methodology. Of course, the oldest and the most proven methodology is experimental methodology, but then sometimes it's limited to the technique which you are using. In many a case, the technique may not be available, a proper technique may not be available, and that's why the detailed analysis may not be possible in experimental investigation. There are certain analytical tool available, like Bernoulli's equation or Huygens-Poiseuille equations. So these are the analytical solution available in some of the fluid mechanics and heat transfer problem. But these problems or these solutions are only for a simple model and with a various, in fact, gross simplified assumptions. Nowadays, there is another branch of physics, which is numerical computational multi-fluid dynamic methodology. So using this technique, basically the detailed analysis is of course possible, because anyway, you are only depend on your computer and your mind. So if your mathematical model is accurate, you can definitely have a detailed analysis of the problem in hand. But then there are certain modeling challenges involved. So maybe in a short while, we'll discuss what are the modeling challenges. And in this numerical technique, basically, there are three steps. I would say that these three steps are a generation of the grid, identification of what you are looking for, which is the physics involved, and finally, the post-processing, the data, a huge chunk of data which you have generated, you analyze it using a proper tool. So as I said, what is CFD? Basically, it's a branch to study various fluid mechanics and the heat transfer problem using the mathematics as well as the computer application. It has basically three branches: development, application, and analysis. Development means the development of the CFD code. Application, usually the companies, industries basically looking for application. They don't want to develop any code. They use available commercial software, and then they use that software for certain application, and they modified certain application or kind of that. The third step is analysis, where people like us, academicians, basically take a problem and then analyze the problem, identify some phenomena, some phenomenological aspect of a certain interesting phenomena. So these three branch is mainly the CFD is, the umbrella of CFD is basically encompasses these three branch: development, application, and analysis. And there is an ample scope in all three field of CFD. As you all know that, again, I'm not going into detail and repeat this, but then why CFD is required? We all know that simulation-based design instead of build and test, because nobody now wants to do trial and error on a prototype kind of thing. They want to save the material, save the time. So the most important and the easiest way is to simulate on a virtual environment, which is computer, and then if everything goes according to the plan, then you build a prototype and then just test it. So a single prototype, and then your product will be on the market, right? So simulation of physical fluid phenomena that are difficult for experiment. As I said, that there are certain things where the experiment is not possible: ships and airplanes, wind, weather, explosion, radiation. So there are many interesting phenomena, cloud bursting basically. So all these phenomena are where in situ experiment is sometimes very difficult and not possible. So these type of phenomena can be understood and investigated using the simulation or basically a virtual environment. So the idea of CFD is to explore the knowledge and explore the flow physics. And this CFD nowadays is basically used in all branch of engineering. You name it, and the application of CFD is there. Aerospace, automotive, biomedical. Some of my students are at present working on blood flow in a artery, flexible artery. So we are trying to analyze how the clotting and other phenomena is taking place. Chemical processing, HVAC and hydraulic is the other area where people are now started using CFD and its application. Right. So how actually CFD works? So as I said that there are various steps in CFD. The first and most important step according to me is modeling. So what actually you are looking for in modeling is you need to generate a mathematical model for the problem in hand, a physical problem in hand, with an appropriate maybe initial or maybe boundary conditions. If it is a transient problem, then you require to identify an initial condition, and if it is only a spatial problem or just a steady state problem, you require to identify basically the boundary condition. So you need to not only identify the mathematical equation and mathematical model, you need also identify what are the boundary or the appropriate boundary for a given physical condition. Apart from that, it's not just a conservation principle, or it's just not just a mathematical model which you are looking for. The modeling also include geometry and domain, because you need to deal ultimately with your physical domain, or you need to deal with the geometry. Sometimes the geometry may be very complex, sometimes the geometry may be very simple. So based on the geometry, you need to identify many things in CFD. So you also need to identify what is your geometry, where it ends, what are the physical boundary, what are the artificial boundary, and so on and so forth. Similarly, identification of the coordinate system is very important. Suppose if you are solving a problem of boiling over a cylindrical road and you use Cartesian coordinate system, it works, but then it's very difficult to analyze if it is a Cartesian coordinate system. Cylindrical coordinate system would be an appropriate choice if the problem itself is a cylindrical in nature. So identification of a coordinate system is also very important. When you select a problem or when the problem in hand, first you need to identify what is your coordinate system, what is the geometry, what are the boundary, mathematical equations, and so on and so forth. Flow conditions, again, we'll discuss shortly that you also need to identify what is the prevailing flow condition, whether it is a laminar, turbulent, compressible, incompressible, and so on and so forth. So as I said, initial condition or the boundary conditions are also very important. And selection of model for a different application. So only conservation principle is not sufficient. You also need to incorporate various models along with the conservation equations. So selection of an appropriate model for an appropriate application is also very important. Modeling, again, as I said, include geometry and domain. So some of the geometry are very simple, flow over a flat plate. So just you need to generate a flat plate which is a square or maybe a rectangle one, right? And this type of geometry can be easily created, like flow in a circular pipe. It's a very simple geometry, and this type of geometry can be easily created. But sometimes the flow is taking place over a very complex geometry. Say, for example, flow in a catalytic converter, or maybe flow over an airfoil, or so this type of geometries are complex in nature, and the complexity in the geometry will also create complexity in generation of the grid, which is a next step of the CFD. In some of the cases, also need to identify that what is the domain size and shape, because if the domain is too large, a huge amount of computational resources or the huge computational power is required. And you need to identify that whether this type of geometry can be handled with available computational resources or not. Because ultimately you are going to solve this problem on a computer. And if the computer facility or the resources is not available, then the certain size or certain shape of the problem cannot be handled. So typical approach would be identify geometry. If geometry is too large, there are ways and means to smaller the geometry. So you need to approximate the geometry, identify whether can I solve the problem in 1/4 domain or maybe half domain, or maybe so somehow you need to reduce the size of the domain. Nowadays, for generating the geometries, there are various CAD, CAE tools are available, and then you can generate your step file or IGS file, and then you can export that file to various solver, CFD solver, like OpenFOAM or maybe ANSYS, Fluent, and so on and so forth. As I said that before you start solving the actual governing equations, you need to identify what you are looking for, whether you are looking for a Cartesian system, XYZ system, or a cylindrical system, or a spherical system. Because ultimately, circular pipe, say for example, it's a cylindrical geometry. Cartesian solution in the Cartesian coordinate will not give you correct picture, or it's very difficult to analyze, because every time the x and y you need to convert into radius, which is x square plus y square under root of x square plus y square. So every time that conversion may not be easy. So better to use an appropriate coordinate system for an appropriate problem. So as I said that Cartesian's coordinate system, cylindrical coordinate system, and spherical coordinate system is very important. Sometimes the coordinate transformation is also required, or the curvilinear coordinate system is also required. Say for example, if you are analyzing the flow over the Pelton turbine or the Pelton wheel, then if you align the coordinate axis according to the geometry of Pelton wheel, then your solution would be very easy to visualize, right? So, but then you need to transform the Cartesian coordinate system or the cylindrical coordinate system into the body align coordinate system. So the coordinate transformation is also sometimes required. So when I say governing equation, it's basically the conservation equation. So ultimately, any problem in engineering can be solved by only conservation equation. You can solve conservation of mass, conservation of momentum, and conservation of energy, and your life or any problem in the engineering can be solved. But the problem is these equations are not just straightforward simple equations. These equations are basically the partial differential equations. They are non-linear partial differential equation. And that is the whole problem with the CFD, that the equation, had it been a simple linear equation, the exact solution would have been possible. But the problem is they are partial, they are coupled equation, they are non-linear equations, and because of that, the exact solution is not possible. And that's why we are looking for an approximate solution, or maybe a numerical solution using a certain tool and technique, which is the discretization of CFD and the CFD tool and technique. And as I said that along with this basic governing equation, so these first three equations are basically momentum conservation equation. It is x momentum, y momentum, and z momentum equation. Suppose if you are solving for temperature, then the energy equation will be added. If you are solving for species, then the species equation will be added. And along with that, the continuity equation or conservation of mass equation is always there. So as I said that along with this conservation equation, you also need to solve certain, or you need to select certain models. So here, cavitation model Rayleigh equations is basically shown, but similar to, if the problem in, depending upon the problem in hand, you need to identify the governing equation or governing model, and then you need to add or solve that model along with the basic governing equations. So as I said that the identification of the flow condition is also very essential. So you need to identify that whether the flow is a viscous flow or inviscid flow. Say for example, if you are solving flow in a Francis turbine. So in Francis turbine, anyway, the Reynolds number is of the order of 10⁵, 10⁶. At that high Reynolds number, anyway, the viscosity does not make any sense. So that's why we are using Bernoulli's equation for solving hydraulic pumps and turbine problem. So inviscid approximation would be a better approximation compared to viscous application. But say, for example, if we are solving a flow of honey, which is highly viscous fluid over a flat plate, or whether it is you are checking wettability or non-wettability of the honey over a banana leaf, then this type of problem is basically a viscous problem where the viscosity cannot be neglected. So depending, as I said, that depending upon the physical problem, you need to identify the flow condition. External flow and internal flow, flow over a bluff body, flow over an aerofoil, flow over a cricket ball, they are external flow, but flow in a catalytic converter, so they are bounded flow. Internal flow are bounded flow. So the wall is basically reducing the instability, and there is a separation of the instability, and that's why internal flow is always simple compared to external flow. But if the flow demands that the flow is external flow, then you need to solve it accordingly. Turbulent flow versus laminar flow. As I said that if the flow is turbulent, chaotic, then you need to use a certain stochastic equation, K epsilon model or Spalart-Almara model, K omega model, to handle the chaos in the flow or the turbulence in the flow. But if the flow is laminar, the Reynolds number is very much lesser, or if the streamlines are not crossing each other, then the flow is laminar. And this type of flow can be handled very easily, pretty easily compared to the turbulent flow. Incompressible versus compressible, the Mach number will identify whether the flow is incompressible or compressible, right? So each flow is having its own characteristic. And based on the characteristic, the governing equation changes, and hence the entire solution methodology changes. Similarly, single phase versus multi-phase. Multi-phase flow, another equation will be added, because along with the flow equation, now you also need to solve interface equation. Similarly, if it is a natural convection or the thermal density effect is there, then accordingly you need to handle the problem. So free surface flow and surface tension flow, chemical reaction and combustion. So what I mean to say is, depending upon the problem in hand, identify the governing equation, identify the model which you are going to use, and then solve it using the numerical tool. So identification of initial condition is very important, because usually the initial condition should not affect the final result. It should be, the final result should be independent from your initial condition, right? So that type of solution is basically called the converged solution. And so the identification of initial condition itself is a big problem, because if you wildly select initial condition, then your convergence may take a little longer time. So to arrive at a quick convergence, the selection of an appropriate initial condition is very much essential. In steady flow, usually the boundary condition makes it more difficult. As I said that for an unsteady flow problem, if the initial conditions are not appropriately selected, then it will take little longer time to converge. So the convergence can be obtained if the initial condition is appropriately selected. Similarly, selection of boundary condition, as I said that there are various boundary conditions, Newman, Dirichlet, Robin boundary condition, famously known as no slip condition, slip condition, inlet and outlet condition. So where the mass is coming in, where the mass is going out, where there is a no slip, where there is a slip condition, where there is a free slip condition. So all this condition you need to identify based on your mathematical model, based on your problem, or based on the physics involved. Periodic boundary condition, convective boundary condition is another recently developed boundary condition, which are very much useful if the flow is periodic in nature, or the convection is happening continuously from upstream to downstream. So as I said, application of initial and boundary condition makes sense, and you need to identify the appropriate boundary condition. Finally, once the geometry is identified, once the boundary condition is identified, I also decided that what kind of mathematical model or governing equation I'm going to solve. Then the next step is ultimately, because as I said, partial differential equation cannot be solved because they are non-linear in nature. So what to do? So in CFD, what we are doing is we are converting this partial differential equations into algebraic equations. And the method of converting this partial differential equation into algebraic equations is called discretization method. So there are various discretization method available. So using an appropriate discretization technique, you can convert your PDE into algebraic equations. And once you have generated the algebraic equations, you can solve that algebraic equation simultaneously using linear algebra. So that's why the solver and numerical parameter comes into picture, right? But most important thing is this discretization technique which you are selecting, that is basically goes along with your grid generations, right? So because that technique has to be in line with the grid which has been generated, right? So the grid generation has to be such that it cope up with a certain numerical techniques. And then as I said, that if a huge number of grid parameter or grid numbers are there, then you require high performance computing, because number of algebraic equation increases as the number of grid points increases, and that will lead to increase the computational power and computational resources. So what are the different discretization methods available? You must be aware of this, that there are different types of discretization method available. Famously, they are finite difference method, the straightforward, it's a mathematical way of discretizing using Taylor series basically. Finite volume, it's a conservation principle based method, integral approach basically. So it is another method for discretization or converting the partial differential equation into algebraic equations. And then finite element method, again, it is another technique specifically used for the irregular meshes or non-uniform mesh. As I said, that each type of method above yields the same solution if the grid is fine enough. No matter which discretization technique you use, ultimately it should result into the same solution. So the finite difference, finite volume, finite element, all these three leads to the same solution, provided if the grid resolution is fine enough and an accurate mathematical model is used. So the spatial derivatives. So in partial differential equation, basically there are two types of derivatives. One is temporal derivative and the other is a spatial derivative, time-based derivative and space-based derivative. So mainly all these derivatives can be converted into algebraic form using Taylor series expansion. So there are various schemes available: second order upwind scheme, central difference scheme, right? For temporal derivatives, explicit and implicit scheme, Eulerian or Runge-Kutta methods are available. So this method is basically converting or this upwind scheme or central difference schemes is nothing but converting your partial derivative into an algebraic equation form. So ultimately, when I say discretization, it does not only mean to just write down equation into Taylor series expansion form. No, you are basically taking into account your grid geometry or grid generation. At the same time, you are also taking into account the conversion of the partial differential equation into the linear algebraic equation using an appropriate scheme, right? So upwind scheme, central difference scheme, explicit scheme, implicit scheme. These are the scheme which is basically used to convert PD into a algebraic equation. So say, for example, these are my governing equation. I'm just giving you an example. How do I convert partial differential equation into algebraic equation? So the first equation is continuity, incompressible continuity equation, 2D. Second equation is my momentum, x momentum equation, right? So let us say I'm just interested in the second order derivative del square u by del y square to convert that into an algebraic form, because this is a partial derivative form and I want to convert that into algebraic form. So let us say I'm solving this equation at mth position, this position, m position. So what I'm looking at is looking at the solution of del square u by del y square at m position. And to achieve solution of del square u by del y square at m location, I'm taking help of two neighbors, m plus 1 and m minus 1, right? And if you apply this Taylor series, again, not directly, you can see this del u by del x can be written as m um minus 1, and del u by del y can be written as plus 1 minus and so on and so forth. Similarly, this del square u by del y square can be written as, it's a central difference scheme, plus 1 minus 2 plus minus 1. So here you can see that this partial derivative is now converted into just a linear algebraic form, but then the number of unknown has increased because u at m plus 1, u at m, and u at m minus 1. At all three locations, u is your unknown variable. So, but then there is not a problem because I can write down similar equation at minus 1. I can write down similar equation at plus 1, right? For the same equation, continuity and the momentum equation. So three unknowns and three equations, and definitely we can solve because the problem is now become closer. Three unknowns and three equations. So ultimately, this equation, the governing equation, you need to solve at each and every grid points. This m and m plus 1 is nothing but my grid location. So at m plus 1, at m minus 1, everywhere you need to solve this governing equation. So what you are actually trying to do is you are trying to convert an algebraic form of the governing equation at each and every grid location or the nodal points. So, and if you collect all this information, right, then you can see that you will have a matrix basically. So u at u is nothing but your unknown variable u1 to umm. Here u1 to umm represent number of grid points. So u at every grid point is unknowns. Now this equation, each equation at each grid point is having certain constant associated with it. Right, you can see that b1 is nothing but a constant, b2 is constant. So this constant is nothing but a coefficient matrix, right? And then you have some right hand side or the source term, which is represented by this right hand side matrix. So actually it is a cross b is equal to c, or a cross b is equal to c. So it's kind of a linear algebra. So if you have n by n matrix, to solve that n by n matrix, I think in a 12th standard we learn that we can use linear algebra to solve this matrix multiplication and come up with the solution. So here to solve this, but the problem over here is the size of the matrix is pretty large, and it depends upon the number of grid points. If there is 100 by 100 grid points, then 10,000 elements will be there in the coefficient matrix, and 10,000 vector will be there in the vector matrix. So the size of the matrix become enormously large as the number of grid points goes on increasing. So we need to use, that's why we need to use computer. Otherwise, you can solve it by pen and paper also. But the problem is the matrix size is huge. So how to solve it? As I said, that linear algebra. So there are various tools available, solvers available to solve this matrix problem. Tri-diagonal, pentadiagonal, adaptive solver, multi-grid solver. So these are the linear algebraic tools available. Using that, you can definitely solve this matrix. Apart from that, there are direct and indirect iterative solvers available. Cramer's rule, Gauss elimination, LU decomposition. they are the direct solver, but problem is they are computationally very, very expensive. Nobody is using this type of technique nowadays. So all the softwares and all the CFD researchers are mainly using iterative technique for solution of this huge matrix or the linear algebraic problem. And as they are iterative in nature, so there are certain numerical parameters which you need to take into account, or which you need to control while the solution is going or iteratively. So this iterative parameter, or the parameter which you need to look for, is under relaxation parameter, convergence limit, right? Residual, you need to monitor the residual and to see that whether the solution is converging or diverging or kind of that. Right. So time step, if it is a unsteady flow problem, then the selection of the time step is also very important. So the iterative, because as the solution is iterative, we need to control this numerical parameter to arrive at the final results. Right. As I said, that the discretization technique depend upon the grid, whether you are using a structured grid, unstructured grid. You can see that the structured grid is a grid in which the boundaries are always orthogonal to the flow, right? But here in the unstructured grid, you can see that there is a tetrahedral mesh, and in this type of mesh, the flow never be or cannot be always orthogonal to the edge or the face of the various control volumes, and that's why discretization becomes little bit difficult in unstructured grid compared to the structured grid. So try to generate structured grids as far as possible. In some simple geometry, you can also go for the coordinate transformation, as I few minutes back only I told. Now your grid would be something look like this, right? The actual grid, let us say that you are solving a flow in a convergent divergent nozzle. So this is a convergent divergent nozzle, and the actual grid would be like this. But then if you transform this grid and generate a rectangular grid like on a zeta eta coordinate, then you solve your problem on a very simple square grid, and then you transfer back the result into the actual mesh. So, but then the transformation equations are needed. So the mapping equation or the transformation equation, grid transformation, is required. Say, for example, Cartesian to cylindrical transformation is r is equal to under root of x square plus y square, or x is equal to r cos theta, and y is equal to r sin theta, is nothing but the transformation equation from Cartesian to cylindrical coordinate. So such a transformation equation is always needed when you go for the transformation, grid transformation. But every time that generation of this transformation equation is not possible. So usually when as and when the transformation equation is available, you should try to transform your grid from the complex grid to the simple grid as possible. And finally, when continuous phase, and the other is basically the disperse phase. So broadly, it is classified as liquid gas flow, or gas liquid flow, gas solid flow, or liquid liquid flow. I'll try to explain at least one example from each. There may be multi-phase flow with a single component. There may be multi-phase flow with a multi-component, like steam bubble in H2O ice slurry is a single component, but there are multi-phase, solid, liquid, and gas all. A multi-component like coal particle in air is having a multi-phase with a multi-component, because coal and air is a two different entities. So all kind of possibilities are there in a multi-phase flow. There is another category called separated or interfacial flow, wherein there is a single interface available throughout the domain, and that single interface separate continuous as well as the dispersed phase. In case of dispersed flow, so there are multiple interface available, and the dispersed phase is continuously mixed with the continuous phase. And volume friction or the size and the geometry, it depends on the dispersion of the flow depends upon the volume friction, size, and shape of the geometry. The common example of this dispersed flow is the boiling in a pipe. Very common example, investigated way back, and people are still investigating it for evaporator design and condenser design. So this type of flow is when the boiling takes place, where boiling or condensation takes place in a pipe. So the flow can be bubbly flow, slug flow, churn flow, annular flow, and so on and so forth. Different kind of flow regime is possible when the boiling happens in the bubbly flow takes place in the pipe, right? So this is basically a gas liquid flow. It's a multi-phase flow, but one phase is gas while the other phase is liquid, right? So common example of gas, some of other common example of gas liquid flow is ship wakes. Cavitation in the ship and submarines can be studied, but then this phenomena is basically gas liquid multi-phase flow, and it's very important to understand the noise, erosion, and erosion of the structure, and so on and so forth. Gas liquid flow, so the previous one was continuously. Gas liquid flow is basically injection of diesel in air. So the injection of diesel in the cylinder is basically gas liquid flow. The cylindrical contain is high pressure, high temperature gas in which the liquid is injected. At the same time, the other application, some of this I have solved during my PhD, which is inhalation of the drug delivery, spray formations. So the entire jet dynamic is basically gas liquid flow. Similarly, liquid gas flow, other applications is cloud formation, inhalant drug delivery. As I said, that these are the liquid gas flow. Liquid flow is basically some of, I think I put some application related to this, mixing and reaction of immiscible liquid, right? Immiscible liquid and mixing, and so in many chemical industry, the mixing of two immiscible liquid is very essential, like mixing of biodiesel into diesel when they are immiscible in nature. So this mixing is very essential in a certain applications, and that type of flow can be understood by liquid flow, right? Solid liquid flow, sedimentation, transport, pollution, erosion, and flood control. So these all are the example of solid liquid flow. Aerosol formation is basically a solid gas flow, solid gas flow. So minute, like coronavirus is basically an aerosol formation. So the study of coronavirus can be done using solid gas flow type of a multi-phase flow phenomena. So what are the modeling challenge over here compared to single phase flow? So here the problem is there are dissimilar metal, gas, liquid gas, solid gas, and so on and so forth, and which is having a different density. So there is a property jump. So there is a property difference between the two phase. Apart from that, there is boundaries where the problem in the single phase flow. Now in a multi-phase flow, there is another boundary. And the problem is it is a mobile boundary, stochastic interface. So the interface between the two phase is continuously moving, and that is actually a boundary. So the boundary itself is moving. And sometimes the condition of the flow is turbulent, which it's basically ice on the cake. It's increase the problem in hand, the difficulty in the problem in hand. So how do we handle all this difficulty? People have proposed various methodology. This is called coupling, multi-phase flow couplings. One-way coupling, two-way coupling, and three-way coupling. Four-way coupling is also possible. So in basically one-way coupling, what we do is we neglect the dispersed phase and just a single phase, the continuous phase is modeled, and some kind of ad hoc modeling is done for the dispersed phase. Two-way coupling is basically there are particles present. The particle is dense enough, and at the same time it affects the dynamics of the continuous flow. And four-way coupling, particle not only affect the dynamics of continuous flow, but they collide with each other. They change the dynamics of the nearby particles also, right? So as you go on increasing the coupling, like one-way to four-way, the complexity of the mathematical modeling goes on increasing, and that also increase the difficulty in the problem in hand. Again, there are fully resolved as well as fully resolved method. Complete physics study is possible. There are certain techniques like Eulerian approach, which is basically used for two coexisting fluid, which is sharp interface and diffuse interface methods. Eulerian Lagrangian idealized isolated particles. So if you are solving particle-laden flow, gas solid flow, then Eulerian Lagrangian method is the best suited method. Lagrangian method, boundary element method, or front tracking method is another way to handle this type of problem. So one of our article published, we identified which method is best suited for liquid-liquid flow basically. And we said that because in our laboratory we are using a level set method, because we have proved that level set method is more appropriate and more easy to handle liquid-liquid interface compared to other Lagrangian or the volume of fluid method, right? So with a just brief introduction on the multi-phase flow, as I said that I'll show you some of the application which I solve for the multi-phase flow. So the first application is solidification. So Professor B. Ravi from IIT Bombay, actually he was solving some problem related to solidification, and then he approached our laboratory, CFD lab at IIT Bombay, to develop a software which can predict the interface during the solidification. So we did that. It's basically a multi-phase flow problem wherein the liquid-solid interface or the two phase is liquid and solid. But when the liquid and solid comes into picture, the problem over here is solid. You don't require to solve any flow equation. In the liquid, you require to solve only flow equation, right? So as the interface moves, there are certain points or certain place where there is a solid, where the flow is not there or the velocities are not there. Only temperatures are required to be solved, and in the liquid you required to solve Navier-Stokes as well as energy equation both. So the methodology is pretty complex. So what we did is we develop a code, and then we solve it using pure diffusion and natural convection. So idea was so when the solidification happens in the liquid, there is always there is a temperature gradient because of asymmetric boundary condition maybe. Now because of this natural convection, the interface does not move symmetric, right? or if it is a planar interface, it does not move planar. It becomes slightly inclined and then it moves. So idea was to identify the effect of natural convection on the interface movement during the solidification, right? So what we did is we first of all validated as we always do, we validated our code with the available literature or the standard results. And then you can see these are the 3 locations. We identified the temperature in the solid, and that temperature is plotted and compare it with the available literature, and it's found it with a reasonable accuracy. So these are some of the solution which we obtain. You can see that in the pure diffusion, if there is no natural convection, then you can see that the interfaces moves pretty smoothly and uniformly. But because of the natural convection, you can see there are 2 cavity selected, L cavity and C cavity. And in L, you can see in L cavity even because of the natural convection, see these white vectors are the natural convection happening in the liquid, and the remaining part is solid. So you can see that because of the natural convection, the interface is not move symmetric, and it end up the mushy zone is basically created not in the center of the object, somewhere in haphazardly, depending upon the strength of the vortex due to the natural convection. Now, it is very essential to identify where this mushy zone is, because if you provide your riser at the place of mushy zone, then you can remove it, but otherwise that will be a defect or the casting defect been generated and due to the improper cooling condition, right, during the solidification basically. So we identified, using our code, we identified that where the mushy zone is, and because of the natural convection, how this mushy zone has been affected and how it propagate into the domain. So we identified in the 2 domain, L shape and C shape geometries. Then we identified the effect of natural convection on the interface movement. You can see that this blue, green, and magenta is basically 3 location, which is shown by the Reynolds number and the Grashof number. You can see that the Grashof number by Reynolds number square, and Reynolds number square is horizontal and vertical axis. So these are the non-dimensional number comes into picture when the natural convection comes. So because of this natural convection, we identified that the interface movement does not remain if the Reynolds number is small and the Grashof number is high. So the natural convection is dominant, and because of the dominance in the natural convection, you can see this, the interface blue one is become slightly slant, while if the Reynolds number is high, then you can see this, or the Grashof number is low, you can see this, that the interface is more or less remain planar, or it's remain the vertical straight. The interface moves pretty smoothly if the dominance of the natural convection is not there. So that we have identified using numerical method and numerical technique. The other problem which we have solved, so we wanted to understand the boiling phenomena and
Hello. चला उसको नेटवर्क इश्यू वापस आएगा. अच्छा, तो and one more left है.
I think there is some network issue. Please stay connected.
By that time, if somebody is having a doubt, then he can write down in chat box. If anyone is having any doubt, please write down in the chat box. ये तो बताओ आज म्यूटेड है लिस्ट में क्यों नाम नहीं दिखा रहा है
Please wait. We are trying to connect to the expert. Once it will be done, a message will be floated. Please wait. Meanwhile, please float the questions if you have any, so that as and when expert will join back, he can answer your queries.
इसमें भी चालू रखना ना।
Now, am I audible?
Yes, yes. Now, Absar, you are audible. Somehow you were disconnected 5-10 minutes back.
I don't know. I was in a. Yeah. कोई बात नहीं. I'll just. In fact, it was in a full screen, and that's why I could not identify that I was
I understood. and
disconnected.
you are
Yeah. So I think I was explaining about this film boiling.
yes. Film boiling. Correct.
Yeah. So as I said that in a film boiling, is the PPT visible now?
Yes, it is visible.
Yes, sir.
Yeah. So as I said, in a film boiling, basically it is a multi-phase flow problem wherein it's a vapor and liquid, gas liquid flow. What we did is our objective was to identify how the Nusselt number changes during the boiling. Now, it actually Nukiyama curve is available where we say that the at critical heat flux, the heat transfer coefficient is maximum. There is a Leidenfrost point where the heat transfer coefficient is minimum. But then actually, if you want to see that how the Nusselt number changes during the boiling, then it is we try to identify that. So you can see this in the bottom, there is a flat plate over which the boiling is, pool boiling is taking place. So the interface is basically a vapor, and the black color line is a vapor in the first figure. Colored contours are basically of temperature. You can see that the generation of bubble in the top animation. At the same time, at the bottom, you can see that the variation of the Nusselt number during the boiling is shown. So you can see that. So what we have did is we identified different zone of boiling. So it's onset of boiling, then propagation of instability, and then 2A is basically necking phenomena. And during necking, you can see that the Nusselt number is the highest one because of the highest heat transfer area over that place. So the Nusselt number is highest during the necking. So through this, the detailed theoretical investigation was possible. As I said, that the role of CFD is to identify the detail analysis, and that what we have identified using the code which we have developed. So this basically is a single bubble. So it's kind of what we did is in a vessel, if there is a boiling going on, then we have concentrated on a single bubble, and then we try to analyze that single bubble and identify that what is happening. But in real life, the boiling is going on very rigorously. So which is called multi-mode film boiling. So there are multiple bubbles generated simultaneously over a flat surface, right? So here you can see that the red one is a flat surface where the heat is supplied. This yellow one is nothing but an interface, vapor interface from where the bubble is being generated. Blue one is basically the liquid or the liquid phase which is existing over the flat surface. And then, as I said, that there are some parameter given, mathematical parameter given. I'm not going into detail of it, but we also consider the natural convection over here, which is the Grashof number is 289. And then these are the non-dimensional number, density ratio, viscosity ratio, specific heat and conductivity ratio, Prandtl number, and latent heat of vaporization. So these are the parameter which you have selected for the simulation. And then if you see the actual boiling, the top figure is basically the interface, and the bottom figure is basically the temperature produced during the multimode film boiling. And you can see this, the multimode film boiling, the actual multimode film boiling happens like this. There are multiple bubbles generated simultaneously. In turbulent regime, this bubble basically also interact with each other. Here we have taken a laminar approximation, so that's why the bubble is not interacting with each other. But had it been a turbulent in nature, the two bubbles also start interacting with each other. So as I said, using this type of analysis, the detailed analysis of the boiling could be possible. Detailed analysis is possible. Detailed theoretical identification can be made, and many physics can be explored if you analyze it correctly. Another problem which we solved is for the cyclone separator. So the previous problem was liquid gas flow. Now this problem is solid gas flow. So this problem we have used Fluent. To solve this problem we have used Fluent, ANSYS Fluent. Now here the cyclone separator is optimized. The geometry of the cyclone separator is optimized. In power plant industry, basically the exhaust gas, the flue gas is basically passed through the Bake filter, and then to the cyclone separator, and then it goes to the electrostatic precipitator. Our electrostatic precipitator is basically a very precious equipment, and to save the load or to reduce the load on the electrostatic precipitator, the cyclone separator efficiency should be higher. Now, to improve the efficiency of cyclone separator means collection efficiency. So it should collect as many particles as possible, solid particle as possible. So to improve this efficiency, the option available is you change the geometry of cyclone separator. So what we did is we play with some of the geometrical parameter of this cyclone separator, like vortex tube diameter, vortex tube length, right? This cone S, which is nothing but a cylinder length, cone height H, HC is also changed. So we change this diameter, change this dimension, and try to see that whether we are getting highest collection efficiency or not. So what do you mean? The collection efficiency is if I inject 100 particles from the inlet, and if 99 particle is collected in the cone area, then the collection efficiency is 99%. And this collection efficiency should be achieved with the least possible pressure drop. Again, the pressure drop should not be too high, because if you go on increasing the collection efficiency, the pressure drop is go on increasing. But the idea is we should not increase the running cost and increase the collection efficiency. So that we obtain using again numerical simulation. You can see these are the temperature, velocity contours obtained across the cyclone separator. A strong vortex has been generated, and that helps to collect the particles in the cone area, or the collection efficiency increases. This is nothing but a pressure contours in the cyclone separator. As I said, that ultimately the running cost should be as low as possible, because if you the increase in collection efficiency, at the same time the pressure drop should be as minimum as possible. So this we attain. This is the figure which shows, although the particle size was only 10 micron, just to demonstrate the particle, a bigger sphere is used over here. It just is for the demonstration. You can see that majority of the particle is collected in the cone area. The collection efficiency, what we got is 76% with the least pressure drop compared to the other cyclone separator available in hand. The last problem which I want to discuss is the gasifier. So in Nirma, basically through DST funded project, Dr. R.N. Patel has developed a gasifier. Now in a gasifier, the problem is you cannot measure everything using experimental setup. Like suppose if you want to measure temperature inside the gasifier, that is pretty much not possible, because the temperature inside the gasifier is of the order of 1000 degrees centigrade. So at the mesh, you can measure the temperature of the wall, right? But then using CFD, we can definitely measure temperature inside the gasifier, and we can compare it with the available literature and so on and so forth. Similarly, the species produced during the different phase of the gasification can also be identified. And that is again not possible. That you can definitely measure the species concentration at the outlet of the gasifier, but inside the gasifier at a different zone, it's difficult to measure the species concentration. So, and CFD analysis can be done, and you can do this. So again, it is a solid gas multi-phase flow. But here the complexity is it's a species transportation also. So you can see that every problem, the complexity has increased. In boiling, it was only mass transport. In particle laden flow in a cyclone separator, that was only air solid air multi-phase flow. In a gasifier, it is air solid gas flow. At the same time, it is the species transportation. So some of the detail of the actual gasifier. This is the dimension of the actual gasifier available in Nirma University. So what we can do over here is an unstructured tetrahedral mesh, because I told you in the starting itself that computational resources also we need to look for. So 5 lakh element we have generated, and that was that maximum we can opt for, and using this mesh. So these are some of the boundary condition. You can see that at these two nozzle, the air is supplied. The mass or the fuel, the wood charcoal or the wood is supplied from the top, and the air is supplied at this zone. Right, it is a downdraft gasifier. Outflow boundary condition, mass flow outflow boundary condition is applied over here, and the remaining thing is nothing but a wall. Right. So this is nothing but vector, velocity contours obtained during the simulation. You can see that the top zone is nearly a dead zone or the passive region where there is not much air movement. The maximum movement, red zone, is where the maximum movement. Your combustion zone will be at the middle. The reduction zone will be at the bottom. So the maximum movement of air and the fuel is taking place in the combustion zone and the reduction zone, and that has been absolutely obtained using the CFD simulation. These are the temperature distribution across the various sections of the gasifier. Now, what we did is we measured the temperature at the wall, and from top to bottom, the temperature is measured. In the different zone, you can see that the drying zone, pyrolysis zone, combustion zone, and the reduction zone is identified, and the temperature is being measured at a different equivalence ratio. So what we did is we also changed the equivalence ratio, and we compare it with the analytical result and found to be experimental result and found to be in a good agreement. So these are the some of the species produced, concentration of the species produced during the entire gasification process. So this is methane production, this is a hydrogen production, H2O production, and the CO production. And finally, what we did is at a different equivalence. So this is the most appropriate outcome or the most elegant outcome of the entire study. So what we did is at a different equivalence ratio, we identify what is the concentration of the different species, right? That CH4, CHCO2, CO, H2. And we also identify the calorific value, because based on this species, those who have studied the gasification process must be knowing that using this concentration of the species, you can find out the calorific value of the producer gas. So what we did is we identified the calorific value of the gas, and at 0.3 equivalence ratio, the calorific value of the gas was the highest. So if you want to operate the gasifier, then the equivalence ratio 0.3 is an optimum condition at which you will get the best quality of the producer gas. That's what we have identified. Now, I think that's it, what I wanted to share with you. Now, if you have a question, I'm happy to answer.
Absar, is there any standard numerical model for solving the multi-phase flow problem?
There are various. In fact, in one of my PPT, I showed there are volume of fluid method, there is a level set method, there is a front tracking method. Okay. Now, different people are using different methods. In my laboratory, basically, we are using level set method. So, okay. Level set method is having certain advantage compared to other method. I'm not saying the other methods are bad or wrong, but level set is pretty simple compared to other method, and we are getting very accurate result with the level set.
Okay.
Yeah.
Any other questions from the participant side?
Mitesh bhai, are you there? Mitesh Vegad?
Yes, Mitesh Vegad is there, I think.
Yeah.
I think he's on mute.
Yeah, he is on mute. Yeah. If you have any further question, yeah, I'm happy to answer it.
Excellent work, Patel. Yes.
Yeah, Mitesh bhai. Yeah. I was just I show your name, and I recall the meeting we had at GTU. Yeah, I think somebody, Meet Parmar, is asking something.
No.
No. Okay. Yeah. Yeah, Mitesh bhai. Yeah, Shah Sahib, are you saying something?
Yeah, excellent presentation, but nice.
Yeah. Thank you.
Yeah.
In fact, the recent problem which I'm handling, like friction stir welding, is a recent one which I'm handling. Like, so I thought that let me share it with you. Yeah.
Lakdawala sir.
Mitesh
Absolute
bhai.
pleasure.
Thank you, Mitesh bhai.
Yep. Mitesh sir, over to you.
All right. Yeah, absolutely fine. So I request Bala to give a vote of thanks, and we will conclude the session then after.
Yeah.
So I would like to thank Lakdawala sir for this so simplified presentation, because as per my knowledge in this field, I have seen the flow chart which has been simplified by you, and I expect that the students, basically the UG student and research scholars, so they must have taken note of it, and it must help them in their future research.
Hope so. Yeah.
All. Thank you so much, sir.
Thank
for
you.
excellent presentation.
Yeah, thank you, Bala sir and Mitesh bhai for inviting me once again. Thanks a lot from the bottom of my heart. Thank you, sir. Thank you. So I'm leaving the meeting, sir.
Yes. Bye-bye.
Yeah, thank you.
Take care.